Hey everybody, let's try this problem. So let's start with solving for the reactions at those supports. Let me just label, I'll call this pin A and roller B. So let me decompose the reactions at the pin, and then this is a roller over here, and this distributed load I'm just going to represent as a single discrete force, and then the magnitude is the area, 1/2 base times height, so that should be 300, located at the centroid of the shape. So let's see, 1/3 of the way this way is 2 feet, and the leftover is over here, 10 feet. Okay, so then let's solve for these reactions. Okay, so in the x direction, AX, the y direction, AY, BY, minus 300. All right, let's sum torque about anywhere over here. Okay, so then let's say that's 12 feet times BY minus 10 feet times 300. Okay, so BY is 3,000 over 12. So 250. Okay, and then AY is 300 minus BY. So 50. And AX is 0. Okay, so then it looks like, okay, AY was 50. BY was 250. And then there's this distributed load like that. Okay, now let's solve for the shear force and bending moment, but using the calculus relationship. Okay, so from here to here, the loading curve is 0, right? Between, let me just jot this down, between 0 and 6, the loading curve is 0. Between 6 and 12, the loading curve is something, right? So let's maybe make an equation for that. So the slope is rise over run, so 100 over 6. I'll just write 50 over 3. And then the y-intercept is over here, negative 100. So the loading curve is minus 100 plus 50 over 3x. This function is this function. Okay, so we got the loading curve here and here. Now, how do you get the shear? Shear dV dx is minus W. So that means between 0 and 6, right, this is 0. This is 0, which means the shear is constant. Constantly what? Okay, so over here, the shear is definitely 0, right? Over here it's 0. But then suddenly we encounter this 50-pound reaction in the positive direction, because if you cut the beam from left to right, since x is positive going left to right, if you cut it like this, this is axial force, this is shear, this is bending moment. So up is positive, so this is positive. So positive 50, just suddenly like this. Here, 50. Like this. Okay, and then from here to here, between 0 and 6, dV dx is 0, which means the shear is constant. Constantly 50. Like that. Okay, but then from 6 to 12, it's different now, right? Because now the loading curve is no longer 0. It's something. So how do we get shear? dV dx is minus W minus of that. So I'll just write minus of that. So plus 100 minus 50 over 3x. Okay, so let's solve for v. So move dx over here. And then we can integrate both sides from where to where? From x equals 6 to some other x that's between 6 and 12. V at x equal to 6 to some other v. So what do we have here? V of x minus v at x equal to 6, which we just said was 50. This is 50. Equals, and then let's integrate this, 100x minus 50 over 3x squared over 2. So I'll just write this as 25 over 3. From 6 to some x. Okay, so let me maybe write that nicer. Okay, so v of x. So this I'll move to the other side of the equation, 50. And then I'll just evaluate this. 100 x minus 6 minus 25 over 3 x squared minus 6 squared. Okay, we could simplify that more, but how about I just leave it like that for now? Okay, so what does that look like? It's some kind of quadratic, right? Because you see x squared. And then the leading coefficient is negative. So it's a parabola that's shaped like this. And then if you can just plug in numbers. As x increases, this decreases. So it's this half of the parabola, not this one. You don't need to know how to just graph in your head. It does make life quicker maybe in some instances, but not entirely necessary. You can just plot it on a computer on your calculator. Okay, and I kind of did one part that I didn't say. At x equals 6, all of this is 0. So at x equals to 6, the shear is 50, which is right here. It matches up. Okay, and then it's this half of a parabola, so it's going to concave down like that. Okay, and then, I mean, we're not exactly sure what it looks like. I'm just saying the shape looks like this. And then at x equal to 12, then we have to do maybe some calculator. So at x equal to 12, let me just punch that in the calculator real quick. Okay, so at x equal to 12, this actually becomes negative 250. So let me make some space on my drawing. Let me just move this. Okay, so that's the function. Again, this is the function when we're between 6 and 12. Okay, so it's kind of, actually it should be a little bit steeper. So it kind of goes like this, because this is supposed to be negative 250. Okay, and then what happens right here? Look, we encounter this positive reaction in the positive direction, so positive 250. So suddenly this goes up 250, which happens to be, right, this is negative 250, so it goes up to 0. So this is shear. Okay, how about bending moment? How do you get the bending moment? So the calculus relationship looks like this. dm dx equals v. So from here to here, between 0 and 6, the shear is 50. Okay, so how do you solve for the bending moment? Move dx over here, and then you can integrate from x equal to 0 to some other x between 0 and 6. M at 0, some other m. So 50 x from 0 to x. Okay, and let's take a look at the picture. There's no couples or anything changing the bending moment instantaneously. So it looks something like, right, so it's 0 and then 50x. It's going up like that. The slope is 50. Oh, this is 0, right? All right, then what happens between 6 and 12? dm dx equals v, but now v is this. Okay, so maybe I should simplify that a little bit. Okay, so something, let's see, 50 plus 100x minus 600 minus 25 over 3x squared plus whatever 25 over 3 times 36. So let's see, 25 times 12. Okay. All right, so, I mean, you could just simplify. Right, let's see. That's minus 300 plus 50, so that's minus 250. Okay. It's a little bit more simplified. Oh, actually, that's pretty good. Okay. And then, how do you solve for m? Move dx over here. And then you can integrate both sides from x equals 6 to some other x between 6 and 12. This is m at x equal to 6. Okay, so then the function, oh, and what is m at 6? At x equal to 6, this has got to be 300, right? From here? So this is 300, right? And then just integrate all that. Minus 250x plus 100x squared over 2 minus 25x cubed over 3, so that becomes a 9, from 6 to x. Okay, so 300, and then, let's see, minus 250, x minus 6, plus 50, let's see, x squared minus 6 squared, minus 25 over 9, x cubed minus 6 cubed. Okay, so, I mean, you can simplify some more, but this is the answer. So at x equal to 6, it's easy to see how all of this just becomes 0. So at x equal to 6, it's 300, which is exactly right here. So it matches up. And then at x equal to 12, if you plug in the number, this whole thing is actually going to be 0. And then just what does it look like in between? Like, you can just graph it on a calculator. But I know that it's cubic like this, and it's going to be some curve that connects from here to here. So it's going to look something like this. Not exactly, but some shape, some curve that I know is going to be concave this way. So then that's it. So this is the bending moment. Oh, this is not the peak, right? This is actually over here. The peak is somewhere else over here. We're not sure where. I mean, that's maybe a follow-up question. Where is the peak and what is the value? You would know how to do that? Like, where is the max? How do you find the max? You take the derivative and set it equal to 0, right? That's how you find the maximum. Okay. All right, we'll leave that for a future semester. Okay, so just keep on practicing using this calculus method. And then let me know if you have questions. I'll see you on the next video.